Okay, now this is what we would call a coordination compound or a coordination complex. Maybe it's called complex because it looks kind of complex, more complex than some of the compounds that we're used to dealing with for the representative elements. By the way, remember what we're focusing on now are the transition elements. What are the other elements called? Remember, the other elements are the representative elements. The elements in the S block and the P block are the representative or the main group elements. And here we're focusing on the transition group elements. Now, what's the terminology here? Well, this basically has two parts, right? This part is what we would call the complex ion. And again, that's easy to remember because it's the complex part. So here we have the complex ion, and this would be its counter ion. So we're thinking of this as an ionic compound. So here this would be called the counter ion, or counter ions, which are not as complex. This is the transition metal, right? Cobalt is the transition metal here. And inside the complex ion, it's bonded to some other things, which are called the ligands. So the things that the transition metal is bonded to inside the bracket are the ligands. So here we have 6 ligands. So the ligands, so what is a complex ion? A complex ion is the transition metal connected to the ligands. The complex ion has 2 portions. It has the transition metal and it has the ligands. And then that's all bound together with the counter ion. So the complex ion is the thing that's in brackets. Okay, now what would we say is the coordination number of this cobalt? So do you remember from lecture what the coordination number for the cobalt would be?
6? Is it the number of ligands?
It's just that simple. That's right. The coordination number is just the number of ligands. We say that the transition metal here is coordinated to the ligands, or it has coordinate covalent bonds to the ligands. So the coordination number here would be 6. For this particular compound. So there might be other cobalt compounds that have different coordination numbers, but this particular compound we can see, so we don't need to memorize this, we can just see it from what I have on the board. There are 6 of these ammonias, 6 ligands attached. So in this particular case, the coordination number equals 6. If you remember what the coordination number means, it should be very easy to figure out the coordination number. The one mistake you wouldn't want to make, you wouldn't want to say that the coordination number here is 9, because we're not counting these 3 chlorines outside of the brackets. Well, the only things we count as ligands are the things inside the brackets. So the coordination number here is 6.
Does it mean that it's how many NH3 attached to cobalt?
That's right. In this case, it's how many NH3s are attached to the cobalt. But in general, it would be how many ligands. In this case, the only ligands are the NH3s. So there's 6 of these NH3 ligands coordinated to the cobalt. So the coordination number just tells you how many ligands are attached to the transition metal. So it's just a matter of learning that definition. For example, what would be the coordination number for this compound? Right. Notice that in this case, we didn't show the counter ion. You don't need to see the counter ion to find the coordination number. Here, the silver is connected to 2 ligands. What would the coordination number be here?
6.
Here it would be 6. So notice that not all the ligands have to be the same species. Here we have 2 different types of ligands, ammonia and chloride, but the total number of ligands is 1, 2, 3, 4, 5, 6. Notice that it makes a big difference whether a substance is inside the brackets or outside the brackets. Outside the brackets doesn't count as a ligand, and inside the brackets does count as a ligand. Here again, I didn't bother showing what the counter ion was because we don't need that for the coordination number. Okay, so there can be different types of ligands. They don't all have to be the same type of ligand. Now let's go back and figure out oxidation numbers, which is also very important. Now, oxidation number is just a way of measuring charge. In chemistry, there's two different ways of measuring charge, formal charge and oxidation number. Those are just two ways of measuring charge. For transition metals, we don't focus on formal charge very much. We focus on oxidation number. Oxidation number is what the charge would be if you approximate all the bonds as ionic. When we're doing oxidation number, we just approximate all the bonds as ionic. Even if they're not ionic, we approximate them as ionic. That's just the convention for finding the oxidation number. By the way, formal charge is what the charge would be if you approximate all the bonds as perfectly covalent. But we won't need to get into that.
For covalent,
yeah, the formal charge is what the charge would be if you approximate all bonds as perfectly nonpolar covalent. That won't apply too much to transition metals. We're going to use oxidation number where we approximate all the bonds as ionic. Now that's just approximation. For other purposes, we actually usually think about the bonds inside the complex as covalent. But for oxidation number, we're going to think of them as ionic. So let's see how that would apply here. Well, what would be the charge on a chloride ion? Let's actually start with this down here. What would be the charge on, actually, let's start with this. So we can start with ammonia. Now, some of the ligands are actually neutral. Ammonia is just a neutral molecule, so this would have 0 charge. So what does the charge on this silver have to be?
0.
Now, in this case, we were told that the charge of the complex was +1.
So then it has to be +1.
Right. In order for the whole complex to have a +1 charge, the silver has to have +1. So you should just have memorized that ammonia is just a neutral molecule that is coordinated here to the silver. So that has 0 oxidation number. So here the oxidation number on the silver would be +1. Let's go down here then. What would be the oxidation number then on these chlorides? Now, this is something you learned in general chemistry. What should be the oxidation number on a chloride ion? -1, because chloride is in the next to last column, so as an ion it tends to gain 1 electron. So each individual chloride would tend to have a -1 charge. So what would the two chlorides together be? They would be -2. What's the charge on the ammonias?
0.
0, as we just learned. So what is the charge on this chromium going to be?
+3.
Oh, the +3. Yeah,
Because we have to have I just told you this has a plus charge overall, so this has to be +3. So now we've determined a more difficult case. We figured out that this oxidation number was +3. Don't confuse oxidation number and coordination number. Those are just two completely different types of numbers that you might be asked about. Coordination number is quite easy. You just count the ligands. Oxidation number is not that hard, but it takes a little bit more work.
So when we're doing the oxidation number, do we start with figuring out what the charge is on the ligands before
Yes.
we do the metal? Okay.
That's right. Because the charge on the ligands is obvious from the periodic table or from outside knowledge. From our outside knowledge, we know this is neutral, and from the periodic table, we know this is negative. But the periodic table only gives you the right charges for representative elements.
Okay.
That's why we have to leave the ligand for last. For this representative element, we can use the periodic table and say this should have a -1 charge. But you can't use the periodic table to predict the charge for the transition elements. That has to be figured out just at the end of the problem. This charge is just whatever it takes to balance the other charges. So that's the method for doing these oxidation number problems. The method is start by putting in the charges for the neutral molecules that you know are neutral, and for the representative elements that you know their charges, and for any other ions where you know their charges. And then you leave the transition metal for last, and that's the balancing term.
Then neutral atoms and
Neutral elements and representative elements and known ions. Well, to put it simply, leave the transition metal for last. Leave the transition metal for last. Because the charge on the transition metal will just be whatever it takes to balance the other charges. And the other charges we should already know from the periodic table or from having them memorized. Like we have memorized that ammonia is neutral.
So first start neutral atoms or representative or
Yes.
in group, but then we'll find whatever in a NH3, for example.
Right.
And then we get transition.
Yes. The key is just leave the transition metal for last. All right. And I would recommend using this notation Notice that we have to distinguish between the charge on each individual ion and the total charge for the group. So what I recommend doing is following the notation I have on the board and putting the individual charges below the elements, and then putting the charge for the group above. For example, notice that here, each of the individual chlorides has a -1 charge. So I put a -1 down below, but since there's 2 chlorides, their total charge is -2. We need to write this number down because this is the number that we used to figure out the charge on the chromium. So I'd recommend putting the charges for groups up above and charges for individuals down below. It's good to do this on paper so we avoid making mistakes.